finishing up our study of just a couple of properties of radicals today, and to start off, just taking a second to check over example 3. It was the conclusion to yesterday's lesson. It's the warm-up for today's lesson, and I'm giving you a second to check it. Does anybody have any questions about what they did? Comments, concerns? Nothing to report. What's up, David? Which one am I looking at? Right here? Okay, so, well, you wouldn't reduce it down because, so you're asking me about this negative 18 right here. There's no square root around it. So it just hangs out there, yeah. There's nothing really you do to simplify negative 18. It just stays negative 18 as part of your answer there. If it had a radical around a different ball game. You can't take the square root of a negative number, yeah. Different number system even. It's an imaginary ball game. Weird. Okay, questions about that? We're good? Okay, so for the new lesson for today, we have one example left in this section, and then it's independent practice. Hey, Tammy, why don't you come on up? No, it's okay. I just want you to be able to see and hear and do this. Okay, so yes, I wanted to take a minute to just have you focus your attention on example 4, and that one's already done. Let me just steal this for a second. Copy, blank, paste, paste. Okay. Example 4. Visually, it is different than the examples that you A, took care of on your homework, and B, that we did in class yesterday. So my question to you is, how do these problems look different than the ones we did yesterday? Jonathan, what do you think? Oh, both of you raised your hands. Frez. I need to come up with like little nicknames or something. The 3 Jonathans in this class is killer. JP. And you'll be John. And then JK. Because my daughter's KJ. Easy to remember. JP, if you will. Oh, there's letters and variables in the problem all of a sudden. So, yeah, we're going to go ahead and apply the same properties we talked about yesterday in order to simplify radicals that have letters in them. So let's go ahead and do that. I'm going to show you sort of a shortcut for how to do this, and then I'll show you why the shortcut works to help you remember what to do. So first things first, let me teach you the easy way to do these problems. What you're going to notice is that underneath the radical, you'll see a series of multiplication. Right now, I see 36 times x squared times y to the 4th. Remember, when there's no symbol in math class, it's safe to assume that we're actually multiplying those things together. Now, since I noticed that there's multiplication, that's kind of my visual cue, if you will, to use the product property. So I'm going to break this radical apart around its products. So, for instance, I know that I can rewrite that radical expression as the square root of 36 times the square root of x squared times the square root of y to the 4th. So that's me just breaking the radical apart using the product property. It's the first thing you write down. Okay, next, I simplify each of these pieces. Why the product property is nice is because it allows us to look at this big radical as just the simplification of some smaller radical parts. So I can go ahead and simplify. For instance, square root of 36. Pretty easy. That's just 6. The square root of x squared, we actually did that a little bit in the last chapter when we talked about perfect square trinomials. Does anybody remember what the square root of x squared was in that last chapter? It's just x, yeah. Trickier. Square root of y to the 4th. Does anybody think they know what it is? JK. It is y squared. Very good. John, how'd you get that? Okay. That is not always how that goes down, though, to be very honest with you. The pattern I'm hoping you start to pick up on is that it's actually division. Check it out. Do you see how I put the 2 back? That was our index. Whenever we take a square root, the index is always 2, even though it's not written. Watch this. 2 goes into 2. How many times? Oh, yeah, just 1. So it's x to the first that comes out. And then 2 goes into 4 twice. So it's y squared that actually comes out. So to simplify the variable parts of your radicand, what you're actually going to do is division. True story. So if we take a look at part B, you can see that it gets a little dodgier because we're taking a square root, but then our exponents are odd. So I have to show you how that works out. I am, step 1, going to break the radical apart into its individual pieces, its factors. So this is the same thing as taking the square root of 18 times the square root of x to the 3rd times the square root of y to the 7th. Then we just ask ourselves, well, how do you simplify the square root of 18? You use the product property again to do that. The perfect square factor of 18 is indeed 9. Square root each piece, you get 3 root 2. Okay. Then, to simplify this middle piece right here, square root of x to the 3rd, I do division. So I ask myself, how many times does 2 divide evenly into 3? And 2 goes into 3 1 time. So what you'll see is x to the first comes out, and then there's actually a remainder. 2 goes into 3 1 time, but there's 1 still remaining. That 1 becomes the exponent of what's underneath the radical. It becomes the exponent for your radicand. So the square root of x to the 3rd is actually x to the first times the square root of x root x. Let's do it again with the square root of y to the 7th. So you ask yourself, how many times does 2 go into 7? Last time I checked, that's 3 times, right? So it's y cubed, and then y to the first is left over. You do not leave me an answer that looks like that. That is what we call a mess. What you're going to go ahead and do is take everything that's outside the radical and leave it outside. And then everything that's underneath the radical gets placed underneath the same radical. This is actually, again, the product property. So our answer looks a little something like this. We take everything that's in yellow, 3x y to the 3rd, and multiply it together. And then underneath the radical, we write everything that's in green. So that'll be 2xy. And that is my answer. That's what the answer looks like. So you're going to have like a radical part and then a non-radical part. Part C, a little bit different because this time around, it's a cube root. But we could still use the product property even when we're looking at the cube root. This is going to break apart into the cube root of 27 times the cube root of x to the 5th times the cube root of y to the 3rd. Cube root of 27, you memorize those 5 numbers, right? 27 is one of our perfect cubes. Very good. I hear it around the room. It is 3. Good. To simplify the cube root of x to the 5th, I just have to ask myself, well, hey, how many times does 3 divide evenly into 5? 3 goes into 5 1 time. So x to the first comes out. Underneath this radical is where I put my remaining factors of x. If 3 goes into 5 1 time, there are still 2 factors of x remaining, so it's x times x, or x squared, underneath. And then 3 goes into 3 1 time, no remaining, so there's no radical part to that. The last step in the process is to kind of pretty up the answer. You can't leave me an answer that looks like that. And that's not a Mrs. Lucas rule. It's not like me being picky, like for real, we don't write answers that look like that. You actually have to simplify it a little bit. So we take what's outside the radical, write that, and what's underneath the radical stays underneath the radical. Because you can't really necessarily simplify the cube root of x squared. Necessarily. Questions about that? All right, one more. We got the fourth root of x to the fifth, y to the eighth, z to the sixth. So I'm going to break that down into the fourth root of x to the fifth, the fourth root of y to the eighth, and then the fourth root of z to the sixth. And then I just basically, from this point, do division. I ask myself, how many times does 4 go into 5? 4 goes into 5 one time. And then there is 1, x to the first left over. Do you see how the exponent of the remainder is actually what's underneath my radical there? For the y's, 4 goes into 8 twice. So that little 2 becomes my exponent for my y. And then 4 goes into 6. So if I'm asking myself how many times 4 goes into 6, that's just one time. And then there are 2 z's left over. So that 2 becomes the exponent for my radicand. Then I take everything that's outside of the radical, here, here, and here, and I'm going to put that together. And everything that's underneath the radical stays underneath. So we have, for our final answer, x, y squared, z, times the fourth root of x, z squared. Questions about that? Okay, now you try. You have that last example to take care of. It's a nice summary of all of the properties in the section. So you have a couple to try on your own, and I can show you those answers in just a minute. I'm going to finish checking off a couple more. So if you want to take a second to check your independent practice conclusion questions before you go on. You don't want to go onto your homework right away if you haven't finished your independent practice conclusion questions. That could be bad. Why would you do a whole worksheet of stuff that you couldn't do, 2 or 3 of? Be bad. What's up? So 3 doesn't go into 2, which means it just stays put. So do you folks want to know why this stuff works?